hear a little beep, that means she turned that thing off. In the Gelb illusion, we have a curtain across here. We've turned off the lights and curtained things off. We've got a projector lighting up a square in a dark room. In a dark room, the square looks white. So in the dark room, the people say it's white. And then we turn on the room lights. Nothing else we need to do. We turn on the lights in the room. And so in the lighted room, the object changes to black. And this tells you right away several things. It tells you that sensation is not just a judgment of luminance. So sensation is not simply a function of luminance, the light to the eye. Furthermore, we know that we increase the luminance, we increase the illumination, so we increase the luminance, and yet the thing got darker. So that really illustrates something. Also, since the color is not a property of an object, reflectance is a property of an object, but the color of the object changes. The same object can have different colors. It makes you realize that constancy is something to be explained. So normally we have perceptual constancies. We're going to say more about that theme, illusions and constancies. Illusions are demonstrations that the constancies are not always satisfied, that things don't always keep the same shape, the same apparent size, the same apparent shape, the same apparent color. But objects can appear to be different or to change. Okay, so what is Wallach's theory of color? Well, Wallach's theory of color explains the Gelb illusion because it's the theory that the color is equal to a function of the luminance of the object divided by the luminance of the surround, or the background. And he does this experiment right here. So his theory of neutral, and what do we mean by a neutral color? We mean the scale. So here's our Fourier decomposition. These are the colors that don't have hues like red or green or blue. Here's the wavelength of the light varying from 700 to say 350 or so. This is the visible part of the electromagnetic spectrum. This is the red end, red, orange, yellow, green, blue, if you can see it, indigo and violet at this end. And colors that consist of equal intensities are the so-called neutral colors. And as we increase the amount of reflectance of the object, so if we're plotting reflectance as a function of wavelength, then we're showing also the amount of luminance coming from the object as a function of wavelength. If that's equal all the way across, these are the neutral colors from black with the 255 shades of gray up to white. Now on the computer monitor, you only need 3 lines, red, green, and blue, to create the impression of white. So that's the computer monitor, just has your white is created there just by 3 lines would be your white. So you can recreate the colors with 3. That's because there are only 3 kinds of color, 3 kinds of cones, 3 kinds of color receptors. There's hundreds of millions of cones, maybe the population of the USA in cones that you have, and rods and cones. You've got 250 or so million in each eye. So last time we gave a diagram of just a few of those rods and cones, but there's millions of them in the back of each eye, about the size of a little postage stamp back there, each of which is responding. And we've got 3 of them, but these are the so-called neutral colors. Another analogy with sound is that if we have all the wavelengths of sound and we generate a sound that has all the wavelengths mixed in together, this is called white noise. By analogy with white light. So white light consists of all the colors, white noise is sound at all the wavelengths. All right. Which is another, you could add that to your table of analogies between vision and audition. All right, so that's Wallach's theory of the neutral colors. Which center disk looks darker? Well, 50 divided by 100 is a half, and 75 divided by 200 is less than half. And so this color is going to look darker than this color, even though 75 is greater than 50. It's a smaller ratio of the background, and so the one on the right is going to look darker. So the right answer here is the one that's going to look darker is the one on the right, because 75 divided by 200 is less than 50 divided by 100. What would subject set x to make the colors match? They would make it 100, because then the ratios would be equal. How many got that? All right, so the people who were here last time, 18 or so that were here last time. All right. Any questions about that, about Wallach's theory of color? Yes.
For the circles, so assuming if they were equal, the 200, 100, 150, so technically the 100 would be darker than the 50, correct?
If, you mean if I turned off the background?
Yes.
Yeah, or if I set them both to 200. So let's say we set them both to 200. Then the 50 would be darker. Right, that's your question.
Okay, so then the least the number, the darker?
So the bigger the number, the brighter it is. So normally as you increase the luminance, it gets brighter, right? So increasing luminance, increasing the amount of light, holding everything else constant, it gets brighter.
Okay.
But the way to get a good black on your TV set, as I mentioned last time, is to turn it on. And the only thing your TV can do when it turns on is give off more light. So if you want to see a good black on a TV screen that looks gray before you turn it on, if you want to see a good black on it, turn it on. And the area that's getting black is giving off more light when it's on than it does when it's off. It's not giving off any light when it's turned off. So if you want to get a good black on your television set, turn it on. And it'll be giving off, in this case, the 75 is darker than the 50, but it's a smaller ratio compared to the background. And if I wanted to make this without changing this darker, so right now it's going to look like a dark gray. If I want it to look really dark, turn this up to 400. That would make it look really dark. That would make it look really black. Okay. Any questions about what's on the board here? Let's go on over and take a look at the connection between sensation. So far we've been talking about sensation, which has to do with the physics and physiology. So when we talk about sensation, we study what is light and sound, what's the chemicals in the air, what is the physics of the situation, how does the physiology detect the presence of light. So we're looking at the rods and cones absorbing light, we're looking at the hair cells vibrating in response to vibrations in the air, setting off neural signals. And we're thinking of these sensations in terms of lightness and darkness, of patches of light and color, after images, for example, that we got of the flag, things like that. Perception, we have a thought balloon now out here. That's where you actually project your sensations into the world and think that you are perceiving something out there, right? So when you think there's a table here, simply because you see it, you've constructed a perception of an object. Now what's the shape of this table? Right here that you're looking at. So you're looking at a table, except for these corners are kind of rounded, rectangular, yes? You perceive this, and yet the sensation in your eye is of a trapezoid. It does, the image on your retina, your sensation is not a rectangle, your sensation is a trapezoid. But you've constructed the theory that this thing is rectangular, even though your retinal image is trapezoidal. So each of these shapes you might perceive. Well, here's an object I have here. It says, ignore the writing. If I change its angle to you, it's producing different shape retinal images. So if I take it and I take this edge and I push it over closer to you, the retinal image is a trapezoid with a longer edge here, and if I turn it this way, it's a trapezoid that way. If I turn it this way, you don't see it as changing shape though, do you? You see this as a rectangle moving around in space. So we have multiple sensations generating one perception, in this case of a rectangle. And so many sensations might go with one perception. But here's the cases where one sensation can go with multiple perceptions. And this shows there's no function connecting the two. Because a function is a rule that assigns to each element in the domain one and only one element in the range. That's the definition of a function. And if you've got many things going to one and one going to many, then there's no function going either direction. All right? So here are cases. So this, I didn't do a very good job of drawing it, but I don't know if I'm allowed to destroy that. Here we go. Yeah. I can fold this up and look at it different ways. So if I put it on a table like this, then this spine is closer to me, right? And I'll call that like looking at it like a tent. So I can look at it like this as a tent, or I can stand it up. I'll call that the book position, where the spine is farther away, so it's standing up. So we have multiple interpretations of the same element. Now this Mach element, it's called the Mach figure. You saw it in the video, right? At the beginning of the video of Zimbardo's Discovering Psychology, there was a ball that went up an endless staircase. And there was also an auditory illusion going boop, 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 sounding like it's going up forever. But if you listened, that auditory illusion didn't go anywhere either. So it's like the auditory going nowhere, but sounding like, so the ball looked like it was going up, 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 up forever. Then the ball went down, and the series of tones sounded like it was going down forever. If you're familiar with the artwork by Escher, Escher has a lot of impossible drawings. So he's taken a lot of examples from perception, put it into his artwork. And it was sort of an Escher-inspired example. He's got the impossible, you can look him up on the internet if you want to see his artwork, like an impossible waterfall where the water runs around going downhill, then it goes over a waterfall and it runs down, and then it keeps going back around again. So the water seems to go downhill forever, and yet it's turning this wheel and getting energy. But the same figure can create two different perceptions. Now you can actually build the real thing and create interesting illusions for yourself. So take a 3x5 card and then go into a room with diffuse light. This here we've got a lot of different lights creating shining on the table. It's good if you have like a room without a lot of complicated lighting, so diffuse lighting. And then you look at it with one eye on the table without reflections. It's good if you don't have shadows or reflection. Look at it with one eye, and it's right now in the tent position, but I see it as standing up. All the colors are going to change, and if I can keep it together and move my head, it's going to have a weird shape, and it's also going to move around and undulate in a strange way. And then you do the opposite. You stand it up, and then you see it. Now it's in the book position, but I see it as in the tent position. And again, I move my head, and then it also is going to change shape and dance around in a weird kind of way. And the colors are also going to be strange. And you can do interesting, it's a little bit difficult to do, but it creates some interesting illusions. But basically, you could see this either of two different ways. Here's another one. When you look at the Neckar cube, and again, you can build the real thing and see some interesting illusions if you get it to reverse, and then you turn it around. It's going to change shape, so you're going to get an illusion of an object that normally is, it's actually rigid, but looks like it's changing shape as you rotate it. When you look at this, it could be that corner A is closer to you, or it could be that corner B is closer to you. So if you just stare at that diagram for a while, you can see it as a three-dimensional object in which B is closer. And then just while I'm watching it, it'll reverse, and then looks like A is closer. So again, one sensation in this case producing multiple perceptions. Or the Faces-Vases is the case where You can see it as two faces facing each other, in which case this region is farther away, and they're closer to you, the two faces. Or you can see it as a vase in which this region is close to you, and this is the background, farther away. So you have multiple interpretations. So again, we've got two perceptual interpretations of the same sensations. And the whole problem of the connection between sensation and perception is to realize that your perception is a theory you have constructed. It's like a scientific theory to account for the observations. So your perception is a construction of the existence of objects that could have produced those sensations. So you could think of perceptions as a theory of your sensations. And it's sort of one way of looking at it is as sort of a best bet as to what's going on out there in the world. So you construct a theory of the world that fits your sensations and is also a good bet for them. All right, now here's a couple of diagrams. Something's happening. Any questions about this while we're waiting for that thing to warm up? Here's some of the drawings from the book. The page number will depend on what edition you have. That's approximately where it is in the book. So Khaled is trying to teach you about shape constancy and size constancy with these diagrams. The artwork is not the greatest. Here's the idea of shape constancy. The door is supposed to look like it did not change shape. This is illustrating the question, when is a door not a door? When it's ajar. All right, Obama was funnier if you saw him on the. Anybody see see him performing? How many saw Obama's joke routine, at least on the internet link? Maybe he had an anger guy expressing when he's mad about something. That's pretty good. All right, you can still see it through the internet if you like. You can find it on YouTube, I'm sure. This one's supposed to illustrate shape constancy up here, size constancy here. That I don't know, that's not a very good diagram, but the hand, as it gets closer to you, the retinal image is getting bigger, but you don't see it, the hand is changing size. Now this diagram isn't very convincing. It looks to me like it came off and it got bigger and closer. I don't know, it looked like it came floating out in space, came off her hand. She doesn't even have any face, does she?
Her hair keeps changing.
Yeah, her hair changed, didn't it? I don't know. All right. Well, anyhow, he's trying to teach you about size constancy there. We have already dealt with color constancy. Objects don't normally change color on you. I'm going to work through a series of explanations, which maybe we will finish today or next time, dealing with such things as why does the moon look larger when it's on the horizon than it does on the zenith? That's called the moon illusion. Calling it the moon illusion doesn't explain it. Moon looks larger. Now I've ordered for you a full moon, but it won't be delivered for a few days. So keep your eye on the moon. On the night of a full moon, the moon is going to rise in the east. That's because we're on the Earth spinning on its axis. I just saw a recent poll of Americans showing that a quarter of them think the sun goes around the Earth. That's bad. That's really bad. Our science education is really bad if a quarter of Americans think that. I mean, no wonder these people get elected in Congress. Anyway, the moon is going to appear to rise because we're on the Earth and we're going that way. We're going to the east at about 1,000 miles an hour if we're at the equator. So we're going that way. You're going to see the moon appear to rise, come across the sky, and about midnight it's going to be to the south, and then if you stayed up long enough it's going to be over in the horizon again. It's going to look bigger when it's on the horizon over here than it does when it's on the zenith. That's when it gets to the high point. All right? If you stay up late enough over on the horizon, it's going to look large again. So this apparent size, anybody taking a picture of the moon incidentally when you saw a giant full moon? What'd you get?
A little bitty.
Nothing, right? Yeah, well, we'll talk about that in a bit. All right. So this is called the moon illusion, and discuss a few theories of it in a bit. Then there's the Mueller-Lyer illusion. Mueller-Lyer illusion, you start off with two lines that are equal. I don't know if those are equal or not. Anyway, we're going to put fins on them. And line 2 looks larger than line 1. So this is known as the Mueller-Lyer illusion. And I want you to measure the Mueller-Lyer illusion at the course website. There's a link there, so let's go take a look at that. So here's the sensation perception demos and tutorials. Here are the perception slides for Psych 101. I want you to take a look at those. I'm going to go down here right now. I'm jumping ahead to the Mueller-Lyer illusion. This one's loading by Michael Bach. Maybe I'll meet him. I've never met him before. I want you to read the description, look for a name of somebody you recognize. Read this here, and then it's part of your homework. I want you to measure this illusion, and then also read this and see if you find a familiar name in the description. So read the text there. Okay, so we can grab this, and so you can grab it with that, and I'm going to slide it across. You tell me when it looks like they're about equal. Is that good?
Mm-hmm.
All right, let's show the result here. I guess we click here. I don't know if you can see it, but here's the little green line where they would have been equal. All right? So, got an illusion here. So you can try to, just do it, measure it for yourself, and then read the description of it. We're going to be talking about the theory behind it in here, but that's what I want you to do there as part of your homework. So that's the Mueller-Lyer illusion. Now this theory is also, we want to explain the Ponzo illusion, and you have probably seen this one in the video, but if you haven't seen it yet, then you'll see it in the video that's assigned today. You'll see it again. So we have two lines that are equal, and then we put railroad tracks or something going like that, and then line 2. So even though the physical sizes are equal, I guess we can write phi S1 is equal to phi S2. The physical sizes are equal. The subjective size 1 is less than the subjective size 2. So line 2 looks longer than line 1. And over here, if the physical sizes are equal, then size 2 is greater than size 1. And that one's known as the Ponzo illusion, and there are lots of examples of that one. You've probably seen it already in the Zimbardo video, and you'll see it in the video that's on later. There's the Baldwin illusion. Baldwin illusion, we have two equal lines, so I'll come on over here. We have two equal lines. I made it less effective than it should be, but line 2 should look larger than line 1. I should have put the smaller ones up there. Would have made it better. But this is the Baldwin illusion. The parallelogram, actually, excuse me, line 1 should look larger than line 2. Let me renumber them then. So, actually, let me do it better. Put this one here, put this one here, put that there. So, line 2, S2 is going to be greater than S1, so this is Baldwin illusion. The parallelogram tabletop illusion. So here's a tabletop. If I draw a parallelogram, two equal lines, and connect them. So if I draw a proper parallelogram, line 2 and line 1 should look the same, but if we make it three-dimensional, we add legs to it, make it a three-dimensional picture, then S2 is greater than S1. Even though the physical sizes are equal. Anybody in here take drafting in junior high school? Anybody take drafting? Thought I saw a nod, yes, back there, anybody? Nobody takes drafting anymore? Actual practical thing that you can get a job doing? Don't teach this anymore, I guess. In drafting, they have two kinds of projections. When you make a three-dimensional, or art class, you know, the art major, you can do what's known as perspective drawing in art, or you can do what's known as an isometric projection. In an isometric projection, lines that are equal are drawn equal in the diagram. And so in some drafting examples, you make isometric projections, which means you have a picture of something, instead of showing just the top view and the edge view and the side view, which is standard in industry for showing an object that you want to create, like on a 3D printer or something. You rotate the object a bit, and lines that are equal are drawn equally rather than in perspective. In perspective drawing, parallel lines converge to a vanishing point. But in an isometric projection, lines that are parallel in the drawing. And lines that are equal in the drawing. It's called an isometric projection. And isometric projections always look bad because those things that are actually equal in the diagram look unequal. Even though you've made equal lines, you've drawn them equally, they look unequal. Well, here's a better version, and this one's better than the version that's in the So, does this look like a parallelogram anymore, or does this line look larger than this line?
Looks larger.
And if I rotate this one over to here, is they the same shape?
Yes, they are.
Here, let's take a look at this. Here's the shape of that one, right? No sleight of hand.
Gotcha.
Fair enough?
So
Same shape. Looks like it gets longer, doesn't it? You're going to see this in the video also described here. And we want to talk about the size of objects in stereograms, in stereogram view. Probably, see, anybody had a Victorian stereoscope, like an old-fashioned stereoscope? It's an object you look into with two eyes, and it's got a slide about this big. You see two pictures of each object, and you put it in there. They came out in the 1890s through about 1920 or so. You can see them now for sale on eBay and in antique shops. And typically they're pictures of like the Taj Mahal and the Grand Canyon and places that people might go someday but never will, you know. And they can see them in 3D because they take two pictures of the same object, one for the right eye and one for the left eye. And then they represent the two pictures, one for the right eye and one for the left eye, and the brain puts the two together in what's known as cyclopean perception. So you have two different images of objects in the two eyes, so it's called stereo vision. And a stereoscope has two pictures, one for the right eye and one for the left eye. And we need to understand what goes on in these pictures. So I want you to first off practice with your eyes the following. So put your thumbs up in front of your face, one farther away than the other, and then look at it with your right eye, and then look at it with your left eye. And you'll see the two thumbs shift relative to each other. This is called binocular disparity. Now you'll notice that the thing that's closer to you is relatively to the left in your right eye, relative to the thing that's farther away. So the near thumb, when I look with the right eye, it's left of where it appears when I look with the left eye. So it shifts one to the other. This is known as binocular disparity. And it's the cue to distance that people use. Now, the object that's relatively to the left and the right eye, relatively to the right and the left eye, is the closer object. So, if I present this on the stereoscope, this is kind of exaggerated, but where this is basically this, except I photocopied it and turned it around, versus this situation, which is exactly the same except I switched the pictures. What's a person going to see, okay, if they get this versus this? So this is exactly that, and that's exactly that, and that is exactly that except flipped over. All right? Everybody clear on that? the brain is going to combine these two. So if I present this to the right eye and this to the left eye, the brain's going to combine these two into one image. Is it going to look like looking down a hallway, or is it going to look like you're looking at a pyramid coming up? So if you didn't have cyclopean vision, let me write that word. There's a famous book called Cyclopean Perception by Bella Ulez. This is named after the Cyclops. You folks know the story of the Cyclops? It's part of the story of Odysseus. There are two great stories that go back to about 800 BC or so. They're attributed to Homer, but maybe they're older stories than that. One of them is, of course, the adventures of Achilles, right, the anger of Achilles about the Trojan War. And the other one's the story of after the Trojan War. It's a sequel, sorry, it's one of the sequels to the Trojan War. That's the story of Odysseus and his trip back. And on his way back, one of his adventures, he runs into the island of the Cyclopses. And Polyphemus is the Cyclops that catches him. And the Cyclopses just have the one eye, right? They don't have two eyes, they just have one eye. And they have horror movies for Cyclopses. Why? Because Odysseus managed to put out the eye of Polyphemus. See, Polyphemus was eating his men, eating a couple of them a day and keeping them prisoner. And Odysseus wanted to get away. They thought, how can we get away? Well, we'll get him drunk and put his eye out. And so there are a lot of horror movies that the Cyclopses make. And when they want to show the perspective of the humans, what do they think humans see when they look at the Cyclops? You know, in the Cyclopses movie about how horrible the humans are. What do the humans see? They see double, right? They imagine that the Cyclops imagines humans see double because they have two eyes, right? And so in the Cyclops horror movie, if you were looking at this in a stereoscope, the human is seeing this. Kind of an overlapped, kind of a double perception, two boxes. But in cyclopean vision, the person has only one view of the object with three dimensions, right? So the two boxes combine into one. The two lines, these two lines combine into one. These two lines, these two. And so the person is either going to see a pyramid coming toward them with the top of a pyramid, or they're going to look like they're looking down a hallway. Is this the hallway or the pyramid? Use your thumbs to figure it out. Go ahead, use your thumbs to figure it out. I don't see anybody picking their thumbs up. That's one way to not get it right, is not use your thumbs. This is the rule of thumb. One object you're allowed to bring to the final exam.
It's the hallway.
Wait a second. Relatively farther to the left in the right eye means what? Closer or farther?
Closer.
Close. Is this relatively to the left in the right eye? And relatively to the right in the left eye? So this is closer than the background, right? Compared to the background. So this is the pyramid coming toward you. And this is the hallway. This is what the right eye sees, this is what the left eye sees in the hallway. If you don't believe me, take a picture, then move the camera to the right 3 inches, take another picture. That's a way to create your stereo views. And there's software that allow you to create stereo pictures, if you like stereo pictures. And there are cameras you can buy with 2 lenses. So you can order them from Amazon or any other dealer of goods like that, so if you want to take stereo pictures. And there's software that allows you to create them in 3D pictures that work with colored glasses. All right, so you can use colored filters to have, so cyan and red glasses, filtered glasses. Cyan is kind of a greenish blue. So cyan, and you can order the glasses online, or you can buy them along with cameras, and the software can create it for you. So anyhow, this is what you do. You may have also had the following stereoscope at home. Anybody have a GAF Viewmaster? That's the kind with the little pictures that come on a wheel, and you put them into the thing, and it's got like a little trigger, and you go, and then the 2 pictures are so small you can't really see the difference between them until you put them in, and then you can switch, close one eye and the other to try to see the difference. And they come with, you know, like Mighty Mouse and fishes swimming in an aquarium and, I don't know, all the same things, the Taj Mahal and all that, all the rest of it. Okay, so a cheap stereoscope is a little plastic. You can probably still buy them at Target or Kmart or someplace. All right. So the question I'm going to be asking you here, though, is that we want to explain is the size. Which is going to look bigger, when it's closer or when it's farther away? Then there's the perceived sizes of after images. So this was the study that you did for homework. How many did after images homework? A few hands coming up. All right, again, only those that were here heard the assignment, although you could have found it on titanium there and done it. I recommend doing this to experience the after images if you haven't done it. And what you discover is that the size of an after image depends on how far away it is. And then size constancy is the fact, again, that was illustrated with that picture of the hand coming closer, that the hand doesn't seem to change size even though it comes closer. When I walk closer to you, the retinal image is getting bigger, but you don't see me as getting bigger. And I go farther away, the retinal image gets smaller, but you don't see me as shrinking. But in the video you saw, when Zimbardo walks across the room, what happened?
He grew.
He appeared to change in size. And that's the Ames room. So size constancy is normally people don't change size, but in the Ames room illusion, people do change size. They have one at the Explorer. Anybody been to the Exploratorium in San Francisco? I recommend it if you haven't been there. Somebody's been there. It's a great museum. I haven't been there many years, but devoted to sensation and perception, basically. So this topic of our course, that's the subject of that whole museum, is the physics and physiology of light and sound and other senses, and all the various illusions, the psychology of perception. And they have a full-sized Ames room there. Now when you go to the Exploratorium, when you get to the Ames room, there are two lines, right? There's kids running through. There's a lot of buttons to push. It's a great museum. There's a lot of things to do, buttons to push, things happen, you run along. And the kids run along from place to place, pushing the buttons, see what's going to happen, and run, push the button at the next place. There's two lines when you get to the Ames room. There's one long line where the people are standing there looking in and going, oh, cool, and they're taking their pictures or videos in there, right? And then there's a short line where the kids are running up, they look in, they go, and they run to the next exhibit, all right? So you want to look in that, go, and then look at the long line too, because it's only one of those two lines where you get the illusion. And they showed you both views in the video. So you saw the two views. In the one video, you see a distorted room. In the other video, you see what looks like a normal room, and Zimbardo is changing size. That's the one where the people are taking pictures and going, oh, cool. And if they're allowed to, they will pose the mother at one end of the room and the child at the other end of the room, so the child is now bigger than his mother or her mother, all right? And that's the picture they're taking the picture of, where the normal size relationship is reversed. Have you been to the mystery spot in Santa Cruz? Anybody been to the mystery spot? A couple of people have been there. And you may have some pictures where people reverse their relationship in size. So they've got that. And they have a kind of a haunted shack there where a ball, you try to push to straighten it out, it's hanging on a chain and yet it's wrong, right? And things roll uphill and all kind of funny things happen. They used to have an exhibit like that at Knott's Berry Farm, and then they took it away. I don't know if they ever rebuilt it, but it was like the haunted shack or something like that it was called at Knott's Berry Farm. It may have been restored. But Santa Cruz Mystery Spot has another case where an Ames room was created basically by an earthquake that shifted all the trees. And so it kind of automatically created an Ames room effect so that you get a good illusion with outdoors. You don't even need to be at the Exploratorium to see it. So we want to explain the Ames room illusion. All right, so let's get started on these phenomena. And I'm going to describe two theories that were proposed for the moon illusion, two ancient theories. One of them by Galileo and one by Claudius Ptolemy. There's a lot of theories you can disprove that are easy to disprove, such as the moon actually changes size. Kind of a silly theory. But here's one that actually was believed. So here's the moon over here, 238,000 miles away. And here's a person looking at it on the horizon, and here's a person standing on the earth looking at it overhead. There's another person looking at it. This is the North Pole. We're looking at the earth from the North Pole. So the earth is turning this direction as seen from above the North Pole. So here it is on the night of a full moon. On the night of a full moon, where's the sun? If this is a full moon, over here on this side, right? Because it's lighting up. So here's the full moon lit up. So the sun is back over here, lighting it up. On the evening of a full moon, the person sees looking to the east, and they see the sun rising. They're running around. Now it's midnight for that person. They see it overhead, and now it's 6 in the morning. They see it setting, and then they're going to ride around into daytime. So this is nighttime for the Earth, and this is daytime for the Earth over here. On the night of a full moon, this person in daytime doesn't see the moon at night. And the moon, of course, is going around the Earth, taking once a month, and that's why you get the phases of the moon. And right now it's not there yet. It's about over here. And I've ordered you a full moon. It's coming up in a couple of days. So it'll be delivered in a couple of days. You'll be seeing them closer and closer to full as you go there. Now, according to Galileo, and Galileo is this guy who was working at Venice, not Venice, California, but Venice, Italy. Anybody been there? It's a great city. You should travel to Venice. You really enjoy it. Very different. It was once a real, for 1,000 years, it was a real powerhouse of the world. Venetians were able to trade silk and spices from the east and become rich. So he was working at Venice, and he heard a description of a Dutch spectacle maker had made a telescope by carving lenses out of light, using the refraction that we talked about before to create a telescope by putting two lenses together. So he ran down to the lab, he began grinding lenses, he made the lenses, he made himself a telescope, and he thought immediate practical implication. You could climb up to the tower of St. Mark's, the big tower that was on the square that fell down in 1908. You could look on out, but it's been rebuilt. You can look out and see the sails of ships coming in, and you know what's coming. You know if it's pepper that's coming from the east or if it's silk that's coming, and you could race down to the wharf to put in your bids, and so you could be the first ones on the dock to buy the goods. So it was very practical. So he knew about refraction. He had built himself a telescope, and he said, what's happening here is, notice there's more air between you and the moon when you're here than here, and the angle is different. And so he said, what's happening is atmospheric refraction is making the image of the moon look bigger. So Galileo by atmospheric refraction believe it or not, this is still in some physics textbooks, but it's wrong. You can disprove it. And another irony is that it had already been disproved 1,000 years earlier, more than 1,000 years earlier. How would you test the theory that the size of the moon has been magnified by the atmosphere, that the image has actually been increased in size? How would you test that? Well, take a picture. You took a picture, thought they were looking for that giant full moon that was really big on the horizon one day, and then you got your picture back and they said, there's no moon in the picture, right? And then somebody said, wait a minute, look at that little tiny, tiny dot, right? There was a tiny little insignificant little white spot on your picture, and you thought, well, that's just a fleck, a little dot. That's not the moon that was so big on the picture. But that was, right? But you can take a picture of the moon on the horizon, you can take a picture overhead, and you can look at the image sizes. And if it's in the optics, it'll show up in the picture. If I take a magnifying glass and I hold it over this and I take a picture of it, the image is bigger as seen through the magnifying glass. So it's going to look bigger through, the picture is still going to show the thing. And as it turns out, the image sizes are the same, so it is not atmospheric refraction. And Ptolemy, the same Ptolemy that had the map of the Earth and that knew how big the Earth was, who also thought that the sun went around the Earth, so he was wrong about that. He looked at the moon through a tube that had a saw blade across it so that he could count the number of teeth in the image, and so he looked at the moon when it was on the horizon and he counted the number of teeth that had been caused. So he's got a saw blade with teeth, and he could measure how big the moon looked, the image of the moon looked, and he waited till midnight and he looked at it and said it's the same. It looks bigger on the horizon, but the image size is the same. And so this is Claudius Ptolemy. Now normally we like Galileo because he immediately adopted, the Earth goes around. Matter of fact, he got in trouble for saying that the Earth went around the sun, they forged documents. The popes wouldn't do that, would they? Yes, they did, and they would. And they later apologized for it, that's true. Like in the 1960s, they apologized. They said, we apologize for setting up Galileo that way and creating these fake documents so we could threaten him with torture. But, we had to save the church. It would have been the end of the church if people believed that, you can't talk about global warming. We can't use those words. And we can't talk about the Earth going around the sun. The sun goes around the Earth. Everybody knows the Earth has to stand still. They have to go that way. So Ptolemy said the sun went around the Earth, and Galileo said the Earth went around. He was right about that, but Ptolemy had a better theory of the moon illusion. He said the reason the moon looks larger on the horizon because it looks farther away. Does that sound backwards? Does it sound backwards that it looks farther away? To many of you it's going to sound backwards, but it's not backwards. So now you have to work your mind through that this is not backwards. Why is it not backwards? The moon looks larger on the horizon because it looks farther away. So let's construct for ourselves a robot that can see and realize what the robot should do. It will be just a simple robot. There it is, just got the one eye there. And on the robot screen, see this robot rides behind Luke in his X-Wing fighter and looks out for the bad guys and he has to shoot back at them. Because what do they look like on his screen when they're coming up behind? So here's what's on the screen. Here's what the bad guys look like, right? Is that what they look like? Which of these is bigger, of these two ships? It could be the same size, right? This one could be farther away. Or, if this one is closer, then is it bigger or littler? Suppose he's looking at this one and this one. So the one that's close could produce a big retinal image. So let's analyze how retinal images, let's use our pinhole model to analyze. So this is the retinal image. And then he's got to have, in his computer, he's got to construct a theory of how big they are, doesn't he? So let's take a look at that. I'm going to use the pinhole model of the eyeball. And let's ask for things that produce the same retinal image. Everything, all these objects produce the same retinal image, don't they? All these objects produce this same retinal image. This little one at this distance produces that image, or a really big one at a greater distance produces the same image. If these are straight, these should be, it doesn't look too straight, but these should be straight lines, right? Because light travels in a straight line. So which is, for the same retinal image, which one is bigger? The one that's farther away. So if you need to construct, if the same retinal image is farther away, then it's bigger. So let's deduce how this robot should work. We know that the ratio, we've kind of already seen this, if this is distance, d, physical distance, and this is size, physical size, we know that physical size divided by physical distance is a constant for all these, right? Phi s1 over phi d1 is the same as phi s2 over phi d2, the same as phi s3 over phi d3, and they're all, these triangles are all similar to this triangle. Let's measure in eyeball units. We'll call this 1, this dimension. And the retinal image, r, divided by 1 is equal to phi s divided by phi d. So r divided by 1 is equal to phi s divided by phi d. Isn't that right? That this triangle is similar to all these other triangles? So that means that phi s is equal to r times phi d. What that means is, for a given retinal image, where r is the size of the retinal image, the farther away it is, the bigger it is. Just a diagram, what I was showing you with the robot. So this is what should be built in to correct for the retinal image. You need to multiply times distance in order to actually know how big it is. And so what Ptolemy is saying in essence is there's a psychological equation corresponding to optics. This is just optics. And all I needed to use is that light travels in straight lines, and using the pinhole model here. Ptolemy is saying, corresponding to this, there's psychology, which is that subjective size is retinal size times subjective distance. And so, if the retinal sizes are equal, so if S is equal